Okay, so as we proceed through this chapter in our book, we're going to hear more and more about vector fields. And so before we get into the math, let's just talk a little bit about what a vector field is and all the places you can potentially imagine these in real life. And so a great example, we actually talk about this in my calculus for biosci majors, imagining blood flow through an artery or a vein, similar to fluid through a cylindrical pipe. If you think about, maybe a skinny, let's go with the vein artery thing, and blood, which is somewhat of a viscous fluid, doesn't flow as smoothly as water. What would the blood flow look like through there? Well, if I did like a little cut through this thing, and one way I could denote, you would maybe expect fluid or blood to flow faster. If it's right in the center, that might be the fastest flow. Whereas when we get towards the edges, little imperfections in the inside wall might block some of the blood flow and make the blood travel slower. So we can kind of model the velocity of blood with vectors. So I'm going to say probably my strongest flows right in here, but as we move further away from the center, maybe the speed's slowing down a little bit in both directions, right? As we get closer to the outside wall, where your blood flow is going to start to slow down. And so you can imagine a whole vector field, all throughout this whole circle here, a whole collection of vectors with different lengths, that together we would call a vector field. Another example, you might see this when you watch the news. I do a lot of times to kind of figure out what the weather is going to be like for the day. And meteorologists will use maps with lots of little tiny arrows, which is indicating how windy it's going to be. That's just one of many measurements, but wind speed and direction is a very common thing in meteorology. And so this is my version of California. So what you might see in a map like this is you might see a bunch of vectors, which is sort of indicating the speed. Maybe you've got, down here in Southern California, an onshore flow of wind. And as you saw with the blood flow, the size of the vector would sort of indicate a really strong wind, right? And then maybe as it gets ashore, it's starting to slow down, not be as strong. There could be some turning motion, right? Maybe sometimes the wind's getting pushed in this direction. I know for Davis is right here somewhere. Quite often we get the north wind. It just seems to a lot of times blow through the valley. There's mountains on either side here, and we get this very strong wind coming from the north into Davis. So that could be shown with a vector field. So imagine all of these vectors together, right? And they could all be going in different directions, but that would be a collection of vectors is just a vector field. That's a real life example. So now we get this starting point here is if you get a vector field, knowing we can write it as a formula like this, where F is a force field or a vector field. And here it's X times I hat plus Y times J hat. And if I want to get a sense what that vector field looks like, what I can do is pick a bunch of points. Obviously, if both X and Y are 0, F is going to be 0. But if I pick an assortment of points, and notice I'm kind of going around the origin, and then just plug those in to generate vectors. And if I plot those vectors, I see this picture where my vectors, since it's really just always formed by your X and Y coordinate, if X and Y are both 1, 1, I'm going to get the vector 1, 1, over 1, up 1. If this is 0, 1, it's going to be 0, 1 going straight up. everything looks like it's moving away from the origin. And of course, as x and y gets bigger, if I chose, for example, 2, 2, now my vector becomes 2i plus 2j, which is going to be longer than this one, right? So it's going to, these vectors will increase in length as we move away from the origin. And likewise, they would be, as we get closer to the origin, they would be smaller versions of that vector. And this is actually sort of a common field that you'll probably see more than once here. A description for this field, since everything's moving away from the origin, we can call it a radial field. And a radial field, sometimes we have the vectors going outward and sometimes we have them going in. If the vectors were going in, we could sometimes refer to that as like a gravitational field. If you've taken some physics and understand the idea that gravity is a force that pulls things inward towards the center of the earth. And they get stronger as you get closer to the center of the earth. This is sort of the opposite. This is that same field we were talking about. So you could think about, like, if you're a certain distance from the origin, your vectors are going to be very small, because again, remember my formula for this field was just x, y. So if I have smaller x, y points, I'm going to get shorter vectors. And I could think of, like, as I look at circles of increasing radius, I'm going to get vectors perpendicular to that circle that are getting even larger. That would be indicative of a stronger force pulling away from the origin. The further away we get, directly away from the origin. Another common field that comes up a lot is something like this. Here my field is given by negative y comma x, so negative y I hat plus x j hat. And if you pick an assortment of vectors, notice I always go around the origin to see what's going on everywhere. I get these vectors, which if I plot them, generates something we would call a spin field. It looks like these vectors are kind of rotating around, spinning around the origin. And the other reason we would call it a spin field is, if you can imagine this is like wind flowing. And if you put a leaf right here in the center, a big leaf, that wind is going to cause the leaf to spin, right? That's a spin field. Now, both of these, the last two, were 2D vector fields. 3D vector fields are a little bit harder to visualize in many cases, but there are some techniques that can help you visualize it. If you think about from 21C, that where we talked about three-dimensional graphs, that the gradient vector, when you calculate the gradient, it always generates a vector perpendicular to the surface. So if I had a sphere, x squared plus y squared plus z squared equals 1, and I took the gradient, remember the gradient's just made up of your partial derivatives. So that would be f sub x, f sub y, f sub z. Take your partial derivatives, I get 2x, 2y, 2z. And if I started picking points in three-dimensional space, kind of similar to the first example where it was just basically x, y, with generated vectors perpendicular outward away from a circle, this three-dimensional field will generate vectors that are perpendicular to a sphere pointing away. So this would be another radial field for a three-dimensional sphere. And of course, as the sphere gets bigger, these vectors get bigger. So that's one way. And you could even imagine it for, this would be kind of a strange field, but suppose I had this paraboloid, f of xy equals x squared plus y squared. That's a very common 3D graph we talked about in 21C. If I move the z over and think of this as a level surface and did the gradient, I'd get the vector 2x, 2y minus 1, which I could certainly plug in points for x and y, and of course z would be -1 always. Or I could just visualize it that this field is going to produce vectors that are perpendicular to my paraboloid. So I tried to draw some vectors, different areas. You can kind of hopefully picture what that vector field might look like. Okay, one more question here. This question, I get this a lot. This question in it's in our book, 16.2, number 5. Here, instead of giving you the vector field, they're asking us to come up with the vector field, the formula for it. And they're telling us the conditions. We want a vector field so that F points towards the origin, not away like our radial field we did before. And they're telling us they want the magnitude to be inversely proportional to the square of the distance from any point xy to the origin. There's a lot there. So let's start with this, like the distance from any point to the origin, because that was the last requirement. If I take a random point, the distance to the origin is x minus 0 squared plus y minus 0 squared, square root of that. But they said the square of the distance, so that would really just be x squared plus y squared. Now, that's going to be part of it. But let's go back to where they said that F points towards the origin. You may recall when we had, on the first example, when we had the, let's back up here. When my field was just x, y, I generated vectors going away from the origin. So it would make sense if you wanted to go toward the origin, you would just make it negative x, negative y. And you can kind of see why. If you pick any point here, x, y, a vector that would get you right back to the origin would be to go to the left x and down y, and that's going to take you right back down to the origin. So that vector itself points towards the origin. But we're not done here. They said something, we have the direction, right? Points towards the origin, but they told us something about the length. They want the length of our vector to be inversely proportional to the square of the distance. So this is also sort of a skill in 21C. If you've got information that they want to create a vector where you have a direction specified and a length magnitude specified, we need to do these in 2 separate pieces. So the first thing we're going to do to get our direction, we want to make sure we want to make this a unit vector so that we can be assured our vector just has a magnitude of 1. And recall, to make something a unit vector, we can just find the magnitude, square root of negative x squared plus negative y squared, which is square root of x squared plus y squared, and then just divide our vector, each part, by the magnitude. So now I have a unitized vector field that is giving me vectors of length 1 that are pointing inward. So now we can address the magnitude part. They told us that the magnitude was supposed to be inversely proportional to the square of the distance. If this inversely proportional thing, what proportional means is it means it's equal, your magnitude is equal to some constant times whatever follows, whatever they say. The example I always use is this. If you've been around Davis, you know there's a lot of bikes in Davis. Would it be true that the number of bikes in Davis precisely equals the number of people in Davis? Probably not. In reality, the number of bikes in Davis is probably equal to some constant times the number of people in Davis. And I would argue that that constant is probably bigger than 1. For example, the number of bikes is 1.5 times the number of people in Davis, something like that, right? So proportional just means it's equal to a constant times whatever they say follows. Inversely means it's the reciprocal. So some constant times the reciprocal of the square of the distance is the way to read that. So since I have my vector, I know the direction is given by this up here, and this is going to be the magnitude. A vector is made up of magnitude and direction. So all I would do is multiply my magnitude times my direction. This is magnitude. I can't spell magnitude. There we go. Let me just rewrite that. Magnitude. There we go. And this is my direction. And so if I bring that in, remember this is to the 1/2. So if I multiply by x squared plus y squared, that's going to be x squared plus y squared to the 3/2. Next video, we're going to talk about how vector fields relate to 2 topics, circulation and flux.